Welcome. Continuing with our part of qualitative analysis, we have completed with the analysis of group 2A in our last lecture. Continuing with that, the analysis of group 2B cations, wherein the centrifugate obtained after separating group 2A and group 2B is taken. Group 2B centrifugate contains polysulfides of arsenic, antimony and tin, and then it is acidified with dilute HCl. Then it is warmed and centrifuged. The centrifugate is rejected and the residue is washed with water. The washings are then rejected. Then concentrated HCl is added to the residue and boiled and further centrifuged. So this is the way in which the separation of group 2A and group 2B, which has been already discussed, is done by the addition of ammonium polysulfide or yellow ammonium sulfide, which separates group 2A and group 2B cations. If after the addition of concentrated HCl any kind of residue is obtained, then that residue will be yellow in color, which is due to the presence of arsenic ions as arsenic sulfide. And in the centrifugate, we need to test for antimony and tin as the cations. This is the chemistry involved in the various tests which we have already performed, that is arsenic sulfide on addition with yellow ammonium sulfide forms soluble complex along with the deposition of sulfur. Similarly, antimony forms a soluble complex with yellow ammonium sulfide, and tin also forms a soluble complex with yellow ammonium sulfide. Till here is the procedure of the separation of group 2B from group 2A. Further, when HCl in the concentrated form is added to the soluble mixture, then arsenic precipitates out as a yellow precipitate, whereas antimony and tin move on into the solution as their soluble antimonyl and tin chlorides. So, in the residue we test for arsenic if the residue obtained is yellow in color, and the centrifugate we will be testing for antimony and tin. So, the centrifugate which is containing tin and antimony is then heated to remove H2S, because H2S is a gas which will interfere in the further analysis. Then this centrifugate is divided into two parts. The first part is taken and excess ammonia solution is added to it, and then some amount of a solid oxalic acid is added. This semi-micro tube is further heated and again H2S is passed through it. If an orange precipitate is now observed, it confirms the presence of antimony as the cation in the mixture. The purpose of adding oxalic acid to the above part 1 of the solution is that oxalic acid masks tin which is present along with antimony as tin oxalate, and hence tin does not precipitate out as its sulfide ion on passing H2S. So, the oxalic acid is a method of separating tin from antimony if both of them are present in the mixture. To the second part of the centrifugate, iron wire is added and then the test tube is heated well. After that, the test tube is centrifuged. The centrifugate is then treated with water and mercurous chloride is added. If upon the addition of mercurous chloride, we observe white precipitates which turn grey, this confirms the presence of tin in the mixture along with antimony. And the chemistry involved is as shown, wherein tin chloride reacts with mercurous chloride to form mercurous ions which deposit as a grey precipitate along with stannic chloride which is formed, and hence the grey precipitates which are obtained are due confirming the presence of tin in the mixture. After we have analyzed group 2 cations in the mixture, We next move on to a systematic analysis of group 3 cations. Before proceeding on to group 3 cation analysis, the interfering anions, if any, present in the mixture need to be first removed. Interfering ions like borate, oxalate, phosphate and fluoride, they need to be removed from the mixture before proceeding for group 3 cation analysis, since they tend to precipitate as the medium changes from acidic to alkaline from group 1 to group 2. So, the removal of interfering anions needs a separate scheme. First of all, we will be discussing with the removal of borate ions from the mixture. For this, 2 gram of the mixture is taken in a crucible and 3 ml of ethanol is added to it, along with 1 ml of concentrated sulfuric acid. This solution is then boiled carefully till the solution evaporates. This solution needs to be boiled carefully because we have added ethanol to it, which is highly volatile and will tend to catch fire if not taken care of. This procedure is repeated 2 to 3 times. In this manner, borate gets removed as volatile triethyl borate and the residue left in the crucible is extracted with ammonia solution. Equation which explains the above procedure is borate ions react with ethanol along with sulfuric acid form triethyl borate, which is highly volatile, and borate ions are thus removed as the volatile compound from the mixture, and now the mixture can be used free from borate ions for the analysis of group 3 onwards. Moving on to the removal of oxalate ions, if any, in the mixture. Since oxalate is also an interfering anion and will tend to precipitate out in alkaline medium, which is needed for the precipitation of group 3 cations. For the removal of oxalate, 2 gram of the mixture is taken and concentrated hydrochloric acid is added to it. The solution is then boiled and solid calcium chloride is added. The oxalate ions precipitate out as calcium oxalate and are centrifuged, and the centrifugate is used for the analysis of group 3 cations onwards. The centrifugate is used and the oxalate ions which have been precipitated as calcium oxalate are rejected. The equation which explains above procedure is oxalate ions along with calcium chloride give calcium oxalate in the form of a white precipitate which can be discarded, and the mixture solution is now free from oxalate ions and can be used for the analysis of group 3. The next interfering anion which needs to be first removed from the mixture before proceeding on for the analysis of group 3 is phosphate. So, for the removal of phosphate ions from the mixture, 2 gram of the mixture is taken and to it 2 ml of ammonium nitrate and 2 ml of zirconyl chloride solution is added to it. Phosphate ions separate out as white precipitate of zirconyl phosphate. This is then centrifuged and the precipitate is rejected, and the centrifugate is analyzed for the cations of group 3 onwards. The equation which goes as follows: phosphate ions react with zirconyl chloride in the presence of ammonium nitrate to form ammonium zirconyl phosphate, which is a form of a white precipitate which can be seen in the adjoining figure, and this white precipitate of zirconyl phosphate is removed, is rejected, and the remaining solution is used for testing group 3 cations onwards. Another ion which is again termed as an interfering anion is fluoride, and it also needs to be removed before proceeding on for the analysis of group 3 cations. So, for the removal of fluoride ions from the mixture, 2 gram of the mixture is taken and to it 2 ml of aqua regia is added. Aqua regia, as we all know, is a mixture of hydrochloric acid in the concentrated form and concentrated nitric acid, and the ratio follows 3:1. The solution is then boiled off to remove H2S. This procedure is repeated 2 to 3 times, and in this way fluoride ions are removed as hydrogen fluoride gas. And the equation which explains this is fluoride ions react with HCl in the presence of nascent oxygen. HCl plus nascent oxygen is a product of aqua regia, which produces HF, which is highly volatile, and fluoride ions are removed in the form of HF from the mixture in this way. And then now the remaining solution is used for the estimation of detection of group 3 cation onwards. Coming to the analysis of group 3 cations. After the removal of interfering anions, if any, from the group 2 centrifugate or directly from the mixture, the group 2 centrifugate is boiled to remove H2S. If the interfering ions have been removed directly from the mixture, then this step of boiling can be omitted, because boiling needs to be done only when we have passed H2S through the solution. So if mixture is used directly, then we can always omit this step and directly use the centrifugate for the analysis of group 3 cations. After this, 2 to 3 drops of concentrated nitric acid are added to the solution in the semi-micro test tube and boiled. This is done to oxidize ferrous ions to ferric ions, since for precipitation further, upon adding ammonia, ferrous ions will form ferrous hydroxide, which is soluble, and hence ferrous ions will not precipitate out, although they belong to group 3, on addition of the precipitating agent. So first, ferrous ions need to be converted into ferric ions so that insoluble ferric hydroxide forms when ammonium hydroxide is added. After that, solid ammonium chloride and ammonia solution is then added till the solution smells of ammonia, or we can also say ammonium hydroxide. Then this solution is centrifuged if a precipitate or a residue is obtained. If a residue is obtained, then it might be white due to the hydroxides of aluminium or chromium, and if the residue is slightly brownish in color, it might be due to the hydroxide of ferric ions. The centrifugate which is obtained over here, in that we analyze group 4 cation onwards. So coming to the residue part, which contains the cations of group 3, which are aluminium, chromium and ferric, the residue is washed with a dilute solution of ammonium chloride. The precipitate is then treated with sodium peroxide solution. Sodium peroxide solution is a mixture of sodium hydroxide and hydrogen peroxide. This is then heated and centrifuged. If a residue is obtained now, then that residue will be reddish brown in color and will be analyzed for the presence of ferric ions. The residue which is obtained for ferric ions is very sensitive in the sense that even a small amount of ferric ions are present in the mixture, or even if an impurity of ferric ions has been introduced into the mixture by using suppose an iron spatula, then also the residue will be obtained for ferric ions even though the ferric ions are absent in the mixture. So a great deal of care has to be taken for the analysis of ferric ions, that is avoiding using a iron spatula for this and using a normal horn spatula. In the centrifugate, we analyze the presence of chromium and aluminium ions. Coming to the residue part, which will be reddish brown in color due to the presence of ferric hydroxide ions. Since iron or ferric ions have reacted with ammonia solution to precipitate out as ferric hydroxide, and the adjoining figure shows us the color of the precipitates obtained, which is ferric hydroxide. The residue is then dissolved in dilute HCl and divided into two parts, that is ferric hydroxide dissolves in HCl. To the first part, we add potassium ferrocyanide solution. If a Prussian blue color is obtained upon adding potassium ferrocyanide solution, then that confirms the presence of ferric ions in the mixture, and the adjoining figure shows us the Prussian blue color. To the second part, we add potassium thiocyanate solution, or even solid potassium thiocyanate can be added. In the observation, if a blood red coloration is obtained, it is a blood red coloration and not a precipitate, then it confirms ferric ions. And a point to be noted here is that ferric ions are confirmed when both the above tests are observed. That means even if one of the tests is absent, then we cannot say that ferric ions is confirmed in the mixture, since in that case the one test which was obtained, the other test which was negative, may be due to some kind of an impurity of iron present in the mixture. So, for confirming ferric ions in the mixture, both the tests should be positive, that is both the Prussian blue color test as well as the blood red color test should be observed. These are the equations or the chemistry involved in the test we have just studied. The ferric ions on reaction with potassium ferrocyanide give ferroferricyanide, which is giving a Prussian blue color. Similarly, ferric ions reacting with potassium thiocyanate give ferric thiocyanate, which is a blood red color. Now, the centrifugate which is containing aluminium and chromium ions is divided into two parts and analyzed for those. To the first part, acetic acid is added and then lead acetate solution is added. If upon performing the above experiment procedure, a yellow precipitate is obtained, it confirms the presence of chromium ions in the mixture. And the chemistry which explains this procedure is chromium ions react with lead acetate to form lead chromate, which is giving a yellow precipitate, and along with that acetate ions are in the solution. To the second part is acetified with dilute HCl and few drops of blue litmus solution are added. After that, excess ammonia solution is also added. If there is an appearance of a blue lake, it confirms aluminium ions in the mixture. A white precipitate in a blue background gives the effect of a blue lake. That is, when blue litmus is added to this solution, then the whole solution turns blue. The presence of aluminium hydroxide, which has been formed on the reaction of aluminium ions with excess of ammonia or ammonium hydroxide, those white precipitates are floating in a blue background of blue litmus, which gives the effect of a blue lake, and this is called the blue lake test for the detection of aluminium ions in the mixture. Now, as we have just seen that for the precipitation of group 3 cations, we have added both ammonium chloride as well as ammonium hydroxide. That is, ammonium chloride and ammonium hydroxide or ammonia is used as a precipitating agent for group 3 cations. Now, the reason for this addition of both the ammonium cations is, when we see the equation, ammonium chloride is fully dissociated to give ammonium ions and chloride ions. Ammonium hydroxide is partially dissociated to give ammonium ions and hydroxide ions. As we can see over here, there is a common ion which is ammonium ion, and therefore due to the common ion effect, since ammonium chloride is completely ionized, it suppresses the ionization of already weakly ionized ammonium hydroxide. Hence, the concentration of ammonium ions and hydroxide ions formed is less, but this concentration of hydroxide ions is sufficient to overcome the solubility product of group 3 cations and not group 4 cations. So only group 3 cations precipitate out over here, since the solubility product of group 4 is much higher and the amount of the hydroxide ions which are produced over here are less sufficient only for group 3, and so group 4 cations do not precipitate out. And this is the reason for the addition of group 3 cations in the case of ammonium chloride and ammonium hydroxide being used as a precipitating agent. Thank you.